All right, coming back in, here is example 6. Again, more of a pre-calculus example because we're looking at the graph of the position function here. But again, we're learning all the different parts of the particle motion problems and the different concepts that you need to know. So it's kind of helpful sometimes to look at the original position graph and to figure out from there what the concepts are, and then come back and we'll use the velocity graph in the next example. All right, so looking at our position, okay, and if we think about this as kind of an actual number line, because the graph, this particle is moving along a horizontal line, and our particle at time 0 is going to be at a position that is 4 inches from some, like, I guess, starting point that's there. If you think of this, we're still going to have this as 0, 1, 2, 3, 4. So here's your positions, left and right of some value, where we're moving along this horizontal line. And we're at position 4 at the beginning of the problem. So we can kind of go here at time 0, time equal to 0. This is where the particle starts. Now, what the particle is doing for the next 2 seconds, notice that the position, S of 1 is 4, S of 2 is 4, that the position remains 4 the entire time. It has a constant position. So really what's happening here is, even though this is at time equal to 4, this particle is not moving. It's actually going to be at this position. Let's do element of, since we're going to include a lot more values on this. It's at that position 4 from 0 all the way up until it gets to 2. Seconds. And so that's how long it's just going to stand there. It's just going to hang out. It's going to stand there. It's not moving. Then what happens is the position starts to change. So your position is going to start to decrease. It's going to be at a position of 0 at 3 seconds. So here's 0 right here. So our particle is going to start moving in this direction, okay? It's traveling at a certain rate of speed, and it's going to hit this position at t equal to 3 seconds. Then it's going to continue traveling, changing its position until it gets to -4. And it's going to continue all the way to -4, and it's not going to hit -4 until 4 seconds into this problem. So here's -3, -4. So our particle continues along its path at this time, heading in this direction until it gets to this position, and it's going to be at this position at t equal to 4 seconds. It's over here at 3 seconds. So it stands here for 2 seconds, then moves this way at a nice, fairly constant speed because our velocity is constant. It's a linear function, so it has constant velocity. So it stands here for 2 seconds, moves at a constant velocity until it reaches over here, and it takes it 2 to 4 seconds to get to this point. Okay? Once you hit this position and this time, 4 seconds, now he's going to change direction. The particle is going to start now moving back up to a position of -2. So the particle, change colors here a little bit. Let's just do the pink. So then the particle is going to start traveling this way, and it's going to hit a position of -2. So it's going to be at this location at t equal to 6 seconds. Okay? And then it's going to stand there for the last second. So, like, again, if I was going to be kind of thorough on this, let's do element of for this one. And we hit this point when we get to 6 seconds, and then we'll be there from 6 up until 7 seconds. So this idea is that, you know, we're moving left, we're moving right, and we have different things. This is a graph of our position, right? So now that we've kind of gone through the graph and the change in position, the position is 4, the position is decreasing. Well, decreasing on the graph really means that you are moving to the left. So this is standing still. Here we're moving to the left. We're coming back up, so this is moving to the right, and then we're standing still again. So that's interpreting that graph. All right, so question, when is the particle moving to the left? It moves to the left starting at 2 and going up until we get to 4. All right, so 2 to 4. If I was going to go because, I would say that since the position function is what you're given, S of t decreases. That's how I know I'm moving left. Now, the calculus reason that we're going to come in with later, I'll kind of put this in parentheses, would be that our v prime of t is less than 0. But since I was given the position curve, you answer it with the position curve. Then when is the particle moving to the right? Moving to the right from 4 to 6 seconds, and that's because S of t increases. And again, if we put the calculus reason here in parentheses, our velocity, oh, you know, I'm putting an extra little, I just realized, S prime of t, the derivative, which is the velocity, is greater than 0. So that would be our reason for that. Now we want to know when is the particle standing still, when you're not moving. So from our graph, we would have our 0 to 2 seconds. And technically, I would probably say brackets on both of these because you have the, what's your position? Your position is 4, 4, 4, 4, 4, 4. So you're not moving, you are standing still this entire time. And you're also standing still 6 to 7. And because S of t is constant, would be our reason there. But again, focusing on the calculus, v of t would be equal to 0 for that entire interval that we're looking at. All right, now scrolling down, let's take a look at the next question. During the first 6 seconds, what is the displacement? The displacement. That's simply your change in position here. Let's label it since I got 2 things I'm going to do. Displacement, we'll abbreviate a little bit. S of 6 minus S of 0. S of 6 is going to be negative 2. S of 0 is going to be 4. So we have minus 6. So if I was interpreting that negative 6, what I would interpret that to be is that the particle is 6 inches left of their starting position at that time. I'll put it here. Particle is 6 inches left of initial position. That's your displacement. And then we want to look at what is the total distance traveled, okay? My total distance, though, is if you think about the picture that I did here in the beginning, is let's take a look at what this particle was doing. It stood still for a little while, so no distance is traveled for the first 2 seconds. Then it travels to the left until it gets to negative 4, and that's for the first 4 seconds. And then it travels to the right and then stands still for the last second. So then the question is, what is the total distance traveled? Well, I stood here for a while, and then I traveled 8 units to the left, and then I traveled 2 units back this way for a total of 10 units or 10 inches. So the total distance would be the distance left plus the distance right. So that's 8 plus 2, which is 10. Notice I'm really doing the absolute value of the displacement. Even though the displacement for the 2 seconds, this displacement is actually going to be negative 8 for the first 4 seconds, the displacement is negative 8, the distance traveled is positive 8. So that's where that absolute value in the formula comes in. And for this problem, I'm just going to go ahead and do it. The velocity at 5, v of 5, if you will recall, that's your derivative of the position function, which is the slope at t equal to 5 seconds. And so since we're given the graph up here, and we're looking at 5 seconds, we're going to be looking at what's happening, what's the slope of this line. So I need this slope. And again, how do I calculate slope? If I don't have a derivative, I could just, it's a line. So I can calculate the slope using algebra. Basically take your point here, 6, negative 2, and your point here, 4, negative 4, and calculate your slope. Your slope for this problem is going to be -2 minus -4 over 6 minus 4, which is going to end up being 2 over 2, which is a slope of 1. So our slope is going to be equal to 1, and then our units, remember this is also known as ds dt, change in position over change in time, so it's going to be our units, sorry, I forgot what my units were, inches per our seconds. Inches per second, 1 inch per second. All right, now looking at the next part that we have here, let's graph the particle's velocity and speed. Now, since velocity is the derivative, right, so v of t is s prime of t, we're going to be talking slopes. So if I look at my graph here, your slope here is 0 for the first 2 seconds. This slope we already calculated was 1. All right, this slope, I'm going to have to use the 0.24 and the 0.4 negative 4. So this slope is going to be -4 minus 4 over 4 minus 2, -8 over 2 or -4. So I have that slope, and again, we have another slope here of 0. And they're constant because these are all linear. So I end up with this nice piecewise. For the first 2 seconds, I would be 0. I'm putting open circles because endpoints are not differentiable and neither are cusp. Then I have a slope of -4 for the next 2 seconds. Slope of -4 for the next 2 seconds. Then we had a slope of 1, which would be about here, for 2 seconds. And then back to a slope of 0. So that would be a picture of my velocity curve. And then speed, remember, speed is your absolute value of your velocity curve, which is you basically make everything positive. 0 does not change, so that would still be there. Your 4 to 6 had a velocity of 1, so your speed is also 1, and this part does not change. The part that changes is this. Your velocity is -4. For this time, your speed is 4, so that's going to flip this up to here. So that would be a picture of my speed graph. All right, and then at what time is the particle moving the fastest? Moving the fastest, I'd probably say that they're talking about speed here and not velocity, because moving the fastest, we don't really care what direction you're moving in. And this would happen at t on the interval of, what do we have, 2 to 4. 2 to 4. And our reason for that, because it would be the max speed is 4 feet per second moving left. And so the left part is what was the negative, and the speed is just the magnitude of what we're doing. Make sure you pay attention to the fact that there's a difference between if I said max speed, which is going to be this 4 feet per second, versus the max velocity, which is going to be 1 foot per second, because technically that is a -4 velocity over there. The min velocity happens to be -4 feet per second. So different things that you're looking at, just be careful with the speed and the velocity. All right, we'll stop that one. And now we're getting ready to jump into calculus, where we're given the velocity curve and we're working with that instead of just being given the position function. But again, just trying to show you different types of scenarios that you might see on the AP. Notice that the first example was algebraic. The second example that I just did right here is more of a graphical example. And so our third example that we're going to look at is example 7, and that is also a graphical example, but notice the difference is I'm given the velocity curve.